All right, we'll get going today. Happy exam week to everyone, and first of two, so get two in a row. What a festive time of year. All right, I do have an announcement on the board for Pre-Veterinary Society, which has been up since a few minutes ago. So if you're interested in that, there's a flyer in the notes. They have one last meeting on Thursday of this week. But other than that, we'll get into the notes today. The title of today's notes is Hodgepodge, because I'm just going to go over a bunch of different things. There was one request from one of your classmates about something to cover, so thank you for your enthusiasm. But the rest of it is just stuff that I thought I had a lot of questions about throughout the semester, or maybe didn't cover in as much detail as perhaps I should have. So we're going to go over some things that will hopefully help get you squared away for some stuff on the final exam, primarily older stuff that we haven't seen in a while. Okay. Also, then the final exam review will start on Wednesday, so it's going to be divided into 3 parts, 34 questions, just like the real final exam, and the breakdown of topics will be very similar to what you'll see on the final exam. And we'll start going over that on Wednesday of this week and continue that for the last 3 days that we're together. All right, and then the last thing also is I sent an email about this, but in case you delete my emails immediately without reading them, the office hours for the next 2 weeks are posted on Blackboard, so they'll be more extended than the normal ones, and so you can check that out, and you can stop by any time during those hours, and I'll be there. There might be some small changes here and there, but likely the schedule that's on there is pretty accurate at the moment. All right, so for any time you want to come by, just check it out on Blackboard and stop by. All right, the first thing we're going to go over, which was the request of one of your classmates, was how to classify different types of solids. So Chapter 9 went through all these different classifications, and it was kind of, it kind of jumped around a little bit in my opinion, but I went through the order that the book was in just to keep us on track for the exam. But now that we kind of have gone through everything, we can come back, put it all together, and give a quick summary of the different types of solids and how we distinguish them and what some of their key properties are. So there are 4 major classifications for solids. I'll start with the one that's probably the easiest to recognize, or I'll start with the 2 that are easiest to recognize. So one is metallic solid. All right, so as the name implies, when you have a metallic solid, you only have one type of thing in there, metal atoms. That's it. Okay, so the lattice points, or the components, as we call them, would be metal atoms. And you have nothing else. Okay, so any metallic element is going to fall into this category. So that means the requirements to be a metallic solid is just to have one type of metal atom. So iron would be a metallic solid, sodium, potassium, any metal that you can think of would fall into the category of metallic solid. Now there are also things called alloys, which are mixtures of 2 metals. We didn't really talk about those, but those would also be classified as metallic solids, where you have 2 different metals mixed together, but all the components of metallic solid are metal only. So then we have to talk about what are the forces that hold these structures together, because as we talked about, solid phases, very often they pack into these very regular structures, and there's certain forces that are responsible for holding the components in place in that structure. So when you have a metallic solid, the forces are, not too surprisingly, metallic bonds. And as we discussed, these are sort of those delocalized valence electrons that bind all the atoms together. We call it a sea of electrons sometimes, so this delocalized bonding that is responsible for holding all the metal atoms together in all 3 dimensions and gives it that very regular structure and that relatively rigid and strong bonding arrangements. So examples of this, as I already said, are pretty much any metal you can think of. Sodium, iron, lead, whether it's a main group metal, whether it's a transition metal, they're all going to be some sort of metallic solid when they exist in the solid state. Now, you can have, as we know, mercury is a liquid at room temperature, and other metals can be liquefied, so in that case they wouldn't be a solid anymore, but when they're in the solid phase, they would classify as a metallic solid. The other one that's very easy to identify, because we've been talking about it for a long time this semester, are ionic solids. So we now know a lot more details about the structures of these solids, the fact that one ion occupies a cubic lattice, or at least of the types that we've talked about, and then the other ion sort of slips into holes in that lattice. We have a lot more of those details now, but we've kind of already knew what the components were of an ionic solid for many times. So the components, the lattice points in ionic solids are ions themselves. So as we said, one ion occupies a regular cubic lattice, either simple cubic or face-centered cubic. The other ion fits into holes in that lattice. And then if you want to know what are the requirements for having an ionic solid, as we've already known for a long time this semester, it's a metal in combination with a nonmetal. Okay, so metals by themselves form metallic solids. Metals with nonmetals form ionic solids, where there's electron transfer, you form positive and negative ions, and those exist. So then the forces that hold together an ionic solid are very strong also. They're called ionic bonds, as we've also discussed in detail. And there are these interactions between particles of opposite charges that are very strong, and they exist in all three directions to give rise to those regular cubic structures that we've now discussed. And we know a ton of examples of ionic compounds. The ones that we talk about from a structural standpoint are going to be pretty simple, like sodium chloride, magnesium oxide, magnesium chloride, things like that. You know, binary ionic compounds are the ones that are going to have those nice simple cubic structures that we've been discussing, but there are many other ionic compounds that would have more complicated structures where we're not going to really get into the details, but all of those classify as ionic solids. Now the last two categories are going to be dealing with substances that are comprised of nonmetals only, and there's two different categories here. Sometimes distinguishing them is a little bit tricky. So the first type are molecular solids. All right, so as the name implies, the lattice points or the components of molecular solids are discrete molecules. All right, so we don't have single atoms at each lattice point. We have a whole group. We have a small group of atoms that makes up a molecule, and so since these are dealing with covalently bonded atoms, they're going to only be comprised of nonmetals. So if you're looking at the composition, the chemical formula of something to try to help you decide which of these categories it is, molecular solids will only have nonmetals in them. They won't have any metals. Metals would fall in one of the other categories. But the big difference here is that in molecular solids, you don't have strong three-dimensional bonding holding everything together. You have relatively weak intermolecular forces. So those can be either dipole-dipole forces if it's a polar molecule, and or dispersion forces. If it's nonpolar, it would only have dispersion forces. So it's going to be those relatively weak interactions between molecules that are holding them in place in the lattice. All right, so if you want to know how to identify a molecular solid and how do we distinguish it from the other category that we're going to talk about, molecular solids, all the polyatomic elements fall into this category. So if it's I2, P4, S8, these polyatomic elements are going to be considered molecular solids. They have discrete diatomic iodines or tetraatomic phosphorus or octanuclear sulfur molecules that are going to be then held together by intermolecular forces. The other types would be any covalent compound that forms a solid. So if we form ice, which is H2O in the solid state, that would be classified as a molecular solid because it has molecules of H2O, and then those are held together by hydrogen bonding interactions in the solid state. The other big classification of solids that deals with nonmetals are called network covalent solids. Now you can't really just look at the chemical formula of a network covalent solid and be able to automatically tell that that's what it is. You kind of have to just remember what are the common network covalent solids. Now in terms of the category, the classification here, the big difference is that the lattice points in a network covalent solid are just the atoms themselves. But just like molecular solids, they only consist of nonmetals, so you don't have any other component besides nonmetals in there. Sometimes they'll have things that are, I guess, classified as metalloids, but they're all things from the right side of the periodic table. But the big difference here is that you don't have intermolecular forces responsible for holding the atom together. You actually have covalent bonds that extends in all directions forever and ever. So the forces that hold these solids together are covalent bonds. And so you can think of a network covalent solid as just an infinite molecule. It's a covalently bonded group of atoms that just goes on forever and ever and ever. And it's those strong covalent bonds that are responsible for holding everything in place. Now, as I said, you can't really just look at the chemical formula and easily be able to tell that it's a network covalent solid. You kind of just have to remember which ones are in this category. So the elements that fall into this category are carbon, both forms of carbon. We talked about graphite and diamond. So both forms of elemental carbon are considered network covalent solids. They're carbon atoms bonded to each other and they extend in all directions. And then the other ones that are in the same column as carbon, silicon and germanium, those are other elements that would form a network covalent solid where you have covalently bonded atoms in all directions. Silicon and germanium have the same structure as diamond. You're just replacing the carbon with silicon or germanium. And then if you had compounds that were combinations of these, so like silicon carbide, which is silicon and carbon in a 1-to-1 ratio, those would also form this type of network covalent solid. And there's really only one type of covalent compound we'll have to worry about that fits this category, and that's going to be SiO2. So we discussed the structure of SiO2 in class, and that's kind of the classic example of a network covalent compound where you have two different elements in the structure, silicon and oxygen. And we taught, and there are of course many others in real life, but this is the only one that we would really expect you to be able to recognize on the test. Because you can't just look at the formula of SiO2 and say, oh yeah, that's definitely network covalent solid. You have to kind of just know that, okay? All right, any questions about classifying the solids? Hopefully this helps summarize and clarify things a little bit. And you know, we'll go over this and try to be able to then recognize just by looking at the formula of a compound what kind of solid structure it would form. Questions? Yeah. H-bonds would be a special type of dipole-dipole force. So I didn't list this separately, but it's any intermolecular force is responsible for holding molecular solids together, whether it's hydrogen bonding, dipole-dipole, or dispersion forces. Anything else? All right, so the rest of the stuff we're going to cover today is sort of blasts from the past, I guess, where we're going back in time. So one thing we had a little bit of difficulty with on the first exam, I guess it was, were trends for ionization energy and electron affinity. So all of us pretty much learned the basic trend. So electron affinity, remember, is an atom gaining an electron to form an anion. Ionization energy refers to an atom losing an electron to form a cation. And we can use the location on the periodic table and the valence electron structure to help us predict relative trends for those two properties. And they both have the same trend. So if we go across the periodic table, they increase left to right. And they increase from the bottom to the top. So as we go in those directions on the periodic table, in general, those properties increase. Now we have to learn things a little bit more in depth than this, though, because there are exceptions to this trend, as what we're going to talk about today. So this is the basic trend. It increases as you go left to right, increases as you go from the bottom to the top of the periodic table. But there are some certain electron configurations that are particularly stable where you're going to have these trends kind of break down a little bit. So the particularly stable electron configurations for the main group, which is where we're really comparing for these properties, are going to be NS2. So if you have a filled S valence orbital, you're going to have a pretty stable configuration. The half-filled P configuration, NP3, and the fully filled P6 configuration. All of these are stable electron configurations, and these are the parts on the periodic tables where the trends are going to break down. Because at these configurations, the atom does not want to lose or gain any more electrons. If you allow me to anthropomorphize atoms, which means turn them in, give them human qualities, the atoms are very happy when they have either 2 s electrons, 3 p electrons, or 6 p electrons. They don't want to gain any more electrons. They don't want to give up any of their electrons. So at these configurations, they don't want to lose or gain electrons. Now, atoms are not sentient beings. They don't have that ingrained in their, in their mind. But you get the idea. They don't want to lose or gain electrons. So this leads to exceptions in the trend for ionization energy and for electron affinity when we go to these parts of the periodic table. So because at these configurations they don't want to lose or gain electrons, you have exceptionally high ionization energies that correspond to those configurations on the periodic table. Right? Because ionization energy is the energy required to remove an electron, If it doesn't want to lose an electron, it's harder for you to do that, so it makes the ionization energy higher. So you have exceptionally high ionization energies for the following groups on the periodic table. 2A, which is the NS2 column, 5A, which is the half-filled P column, and 8A. Now, 8A is not really an exception. You expect this to be higher anyway because it's furthest to the right, but it still is even higher than you would normally predict. Okay? So it doesn't really lead to any exceptions in the trend, but it's still higher than you would predict. And then finally, for electron affinity, you have sort of the opposite thing, which is where you have exceptionally low electron affinities for those groups, because electron affinity is the desire of an atom to gain an electron, and they tend to be negative values, exothermic enthalpy changes. And when you get to those configurations, they don't want to gain any more electrons, so they have a lower electron affinity, which means they're less negative, or in some cases even positive values for electron affinity in these groups. All right, so the same groups in the periodic table are going to be where the trends sort of break down. So if we look what happens then as we go across the periodic table, I'm going to draw a graph here. So in blue, I'm going to show the ionization energy trend. All right, so what happens as we do this? So we have group 1A. Let's say it starts down here. This is an arbitrary scale, of course. As we move to the right, we expect the ionization energies to increase. Now, as I said, when we get to group 2A, that's a stable configuration. This is NS2. And so at this column of the periodic table, the ionization energy is higher than you would expect it to be because it doesn't want to lose any more electrons. So this one is higher. It's up here somewhere. And I want to put that, let's say, there. So that's one of your points. And then when we go from group 2A to group 3A, the ionization energy tends to come down a little bit. Okay, because this one is exceptionally high. So group 3A would be somewhere here. And then we go sort of steadily up for group 4A. But then once again, group 5A is another one of those stable configurations. NP3, so that one comes in a little bit higher than you'd expect. Which means there's usually a discontinuity between 5A and 6A, where 5A is higher than expected, which means it tends to be a little bit higher ionization energy than group 6A, which is the P4 configuration. And then it increases, and then it really blows up at the noble gas configuration, because P6 is sort of the king of all configurations, and it's going to be really high. But we would expect that to be the highest anyway, because it's furthest to the right, so it doesn't really cause any exceptions to the trend. It's just way higher than we would normally predict. So there is a general linear or increasing trend from left to right, but a few of these, group 2A and group 5A, sort of lie off the basic trend, and they're above that, and that leads to these discontinuities in the trend that we should be familiar with. Okay, so you can't just use the left to right trend as in saying that it always increases monotonically. It's not a monotonic increase. It sort of fluctuates a little bit. In most cases, it increases, but there's some that are off the line a little bit. And then if we do it for electron affinity, we get our blips in the trend occur at the same spots, but they're going to be sort of the opposite effect on the trend. So red is going to be electron affinity. Remember, electron affinity is a negative number, but when we say that it's a high electron affinity, that means the number is more negative. So we're just sort of talking about the absolute value of that. So let's offset this a little bit. Start it here, let's say. All right, so let's say that's the electron affinity for group 1A. Now what happens is when we go to group 2A, this is a very stable configuration, so it doesn't want to gain any more electrons. Group 2A has an exceptionally low electron affinity, so it would go, these ones are really low. I mean, if you look at the actual numbers, it's way different. So it's like somewhere down there, and then they're going to sort of pick back up. It's a little bit hard to compare the S block and the P block to each other, so we're not really going to ask you to do that, but the basic trend is that it increases and as you go across. But again, once we get to group 5A, it's way off the trend and it's way lower because you have, again, a stable configuration. It doesn't want to gain any more electrons, so it has a very low electron affinity. And then we have an increase, 6A, 7A. Now we don't even really talk about electron affinities for the noble gases, which is group 8A, because those are exceptionally low and ill-defined. So that's going to be way down here also. So the electron affinity is even more discontinuous. Now again, you have sort of this basic trend left to right, but the important exceptions are 2A and 5A, which are way lower than you expect them to be because those are stable configurations. All right, so when you're comparing electron affinities and ionization energies, be aware that it's not a perfectly smooth trend. Radius, it is a perfectly smooth trend. You don't have to worry about any blips in that one. Electronegativity, same thing. There's no real exceptions there. But for these two properties, ionization energy and electron affinity, you have to be aware of where the increase is not as steady as you might normally expect because of the stable configurations. All right, questions on that? Okay. Now, another very important topic for this course, and now is a good time to sort of summarize it, is determining moles. Because pretty much everything we did from chapter 4 through chapter 8, or sorry, chapter 5 through chapter 8, starting with, stoichiometry, moving on through solution stoichiometry, gas laws, enthalpies, all that stuff requires moles of substances as kind of the key linchpin. Okay, so much of what we do in chemistry, and it's not going to end in this course. If you take chemistry 2, you'll still be dealing with moles all the time. So much of what we do requires us to calculate moles of substance, and we should be familiar with the 4 ways that we can do this, because moles is not a very convenient unit to go into the lab and measure out, but it's related to some other quantities as well. Now, there's a relationship. The real definition of a mole is that it's 6.022 times 10 to the 23rd entities, whatever entities make up that substance. So if we want to relate that to the number of entities, this is also not a very convenient thing to measure, because counting out a mole of molecules or atoms, even if it was possible, would take forever, so we're not going to really do that in the lab. But whenever you have a substance that's made up of atoms or molecules, there's this relationship where 1 mole of substance is consisted of 6.022 times 10 to the 23rd of whatever makes it up. So if it's an element, that means it's 6.022 times 10 to the 23rd atoms. If it's a covalent compound, that means there's 6.022 times 10 to the 23rd molecules. So whatever composes that substance, if you want to convert from moles into the number of entities, you're going to multiply by that number. And if you want to convert from the number of entities, so the number of individual atoms or molecules, to moles, you divide by 6.022 times 10 to the 23rd. Now, as I said, this is not a very practical thing that we use in the lab, but it's really the basic definition of a mole, and it's something we want you to be familiar with and where that concept comes from. All right, so moles is just a counting number, and it tells you that you have this many atoms or molecules or whatever it is that makes up your substance. All right, so that's the sort of the one we started with. And then the one that we probably use most often is the relationship between moles and mass of substance. And if any of you, you've probably done some chemical reactions in the chemistry lab if you're taking the lab portion of this, or if you start joining a research lab later in life, this is typically the way that it's done. If you want to measure out an amount of substance, the most straightforward way to do that for most things, especially if they're solids, is to just weigh it out, measure the mass of it. And so the relationship then between mass and moles, if we want to convert from mass to moles, we divide by the molar mass, which is the mass of 1 mole, and if we want to go the other way, we multiply. All right, so that one comes up all the time. We even saw it in the gas law section, where if we have the mass of a gas, we can relate it to the moles, and then we can relate that to density and so on. So this one, you'll see it a lot, but especially when you're dealing with chemical reactions where you're weighing out amounts of substances and reacting with each other. In Chapter 6, the new relationship that we introduced was called molarity, which relates the number of moles to the volume of a solution. So very often when we're doing reactions in solution, we don't measure out the individual substances, we measure out solutions of those substances where it's dissolved in some solvent, usually water. And so if we want to relate the volume of our solution to the moles of substance, we use molarity. So we multiply the two if we want to go from volume to moles. And we divide by molarity if we want to go in the other direction, from moles to volume. All right, because molarity is moles per liter, so if we know the liters of solution, we can relate that to the moles of substance using that ratio, moles per liter. And that was what came up a lot in Chapter 6. And then finally, what we've learned most recently in Chapter 7 is the ideal gas equation. So for ideal gases, the pressure and volume are both related to the number of moles. And this comes from the equation PV equals nRT. So there's different ways to use this equation depending on what information you're given and what you're actually trying to do with the problem. But using this relationship PV equals nRT, if we know the pressure and volume of a gas, as long as we have the other parameters, we can relate that to the moles of substance. And we saw that at STP, standard temperature and pressure, there's some more specific relationships involving those as well, but they all come from this same equation, PV equals nRT. So that's a very important overarching concept for a lot of the types of problems we do, because very often, even if it's only a small part of the problem, you have to calculate moles. And if you can't do that, you're going to be sort of stuck at the beginning and not able to progress with the problem. So questions on that concept before we see a couple of example problems related to this. All right, so one type of problem that we sort of had a little bit of trouble with throughout the semester is, it looks very simple in concept, but there's a step here that many of us forget. So let's say we have 0.1 moles of ethane, which has a formula C2H6. How many atoms are in there? Now the part that a lot of people, I guess, forget is that when you're calculating number of atoms, if you start with the 0.1 moles of C2H6, remember that we can relate this to the number of entities that make it up by using Avogadro's number. So many of you will do the first step correct. We'll just multiply by Avogadro's number, but they'll stop there. But remember that this 6.022 times 10 to the 23rd is the number of entities that make up C2H6. C2H6 is a covalent compound made up of carbon and hydrogen. So when you multiply by Avogadro's number, what you're getting is the number of molecules of C2H6, not the individual number of atoms. So there's that many molecules in 1 mole of C2H6. But if the problem asks for how many atoms are there, we have to do one more step. Because each of these molecules, C2H6, has 2 carbons and 6 hydrogens. That's a total of 8 atoms. So we have to multiply it by 8 atoms per molecule. All right, so when you're using this sort of factor label method, it's very helpful to precisely label what each term represents, not just try and multiply numbers together until you get the right answer. And then make sure that you know exactly what it represents. So this is molecules per mole because C2H6 is a molecular compound, not an element. So we have to do that extra step, and we would get 4.82 times 10 to the 23rd. All right, because I guarantee if we had a multiple choice problem like this 0.1 times 6.02 times 10 to the 23rd, that would be one of the answer choices. And so if you forget to do this last step, you're going to pick the wrong one. Questions? Okay. Now the more involved application of moles is going to be doing stoichiometry problems. And this is one variation on a stoichiometry problem that we had it on the last exam, I think it was, or on exam 2, and we had some trouble with it. It's not this exact problem, but the same kind of concept. All right, so if we're producing aluminum oxide by reacting aluminum with excess oxygen, how many grams of aluminum oxide can be made if the percent yield is 50%? Okay, so for any stoichiometry problem, we start with a balanced chemical equation. So we're taking aluminum plus oxygen to make aluminum oxide. And remember, aluminum forms +3 cations. It's not the most obvious one, but we should remember that one. It's a S2P1 configuration. So the formula for aluminum oxide is going to be Al2O3. All right, it's 2 + 3 cations with 3 - 2 anions. So we have to make sure we can balance the equation and get the formulas of the compound correct. But then from there, we have to put some coefficients in. So we'll put a 3, 4, and 2. So if we want to balance it with whole number coefficients, this is the smallest way to do it. So we start with a balanced chemical equation, and then the other key part of this problem is that we're given the percent yield, 50%. Now in a lot of problems you're asked to calculate percent yield, but here it's given to you. So percent yield, remember the definition of this is actual yield divided by theoretical times 100. So in this problem what you're really doing is we're trying to calculate the actual yield, okay, because we're giving you the percent yield, it's 50%. We're giving you the amount of reactant that we're starting with, and we're going to use that to then calculate the actual yield of this reaction if we know the percent yield ahead of time. All right. Now, you don't usually know the percent yield ahead of time. If you know what you're expecting it to be, you can calculate what the expected actual yield is going to be. So then what we have to do is calculate theoretical yield, because this is going to be our unknown. We're going to have to calculate this and use that with the known percent yield to figure it out. So when we do the stoichiometry calculation using moles and all those things, what we're always calculating is theoretical yield. You can never calculate an actual yield for a chemical reaction. You can only calculate theoretical yields. So we have 3 grams of aluminum. We have excess oxygen, so we're just going to start with aluminum because that's our limiting reactant. We have to convert this into moles. The first step in any stoichiometry problem is to convert to moles. So we use atomic mass because we're given the mass in grams. From the periodic table, the atomic mass of aluminum is 26.98. So that gets us into moles of aluminum, and then once we want to find the relationship of that to the other substance, in this case the product aluminum oxide, we use the coefficients from the balanced chemical equation. So there's a 2 in front of Al2O3, there's a 4 in front of aluminum. That means we're forming 2 moles of aluminum oxide for every 4 moles that react. And so if we multiply by this ratio, 2 moles of Al2O3 per 4 moles of aluminum, that'll cancel out moles of aluminum. And then finally, we use the molar mass of aluminum oxide, which I didn't give you here, but that's going to be 101.96. That's the molar mass of aluminum oxide, and that's grams per mole to get us back into grams. All right, so what we get is 5.67 grams. Now this number here is the theoretical yield. This represents the maximum amount of product we can form, or alternatively it represents the amount of product we would get if the yield was 100%. But here we're telling you that the yield is 50%, so the actual yield is going to be 50% times the theoretical yield, which comes out to 2.83 grams. So that would be choice A. All right, so choice B, which is 5.67, that's the maximum theoretical yield if you had 100%. But if we tell you that the actual percent yield is 50%, you're only going to get half of that, 2.83 grams. So just be aware that when we have percent yield, we can work backwards and give you the percent yield and have you solve for the actual yield. It kind of can work both ways. All right, questions on that one? All right, so the next thing I want to go to, and it kind of all relates to the last few things I want to talk about, are related to chemical bonding. So chapter 3 in this textbook was all about bonding, and we talked about some properties of bonds, and the 2 major properties that we talked about were bond length and bond strength, and the 2 have a close relationship to each other. So we had a lot of problems in this section that asked you to predict the ordering of bonds in terms of their bond length, or the ordering of bonds in terms of their bond strength. We want to understand the factors that influence those. So bond length is just the distance between 2 atoms when they're bonded together. It's how far apart they are in that bond. And there's 2 factors that are going to determine the bond length, and we're going to want to think about these 2 factors if we're comparing bond lengths. So the first, and usually the most important one, is bond order, which is whether it's a single, double, or triple bond. And there's sort of an inverse relationship. So the single bonds are going to be the longest. That would be if you have 2 atoms with just a single pair of electrons that's shared. Single bonds are the longest. Those are going to be longer than double bonds, which would be 2 shared electron pairs, and those are going to be even longer than triple bonds. All right, and this tends to be the biggest effect, bigger than what we'll talk about for the next factor. So first, look at the bond order. When you're trying to find, the longest or the shortest bond in a list of bonds, if you're trying to find the longest bond, zero in on those that are single bonds. And if you're trying to find the shortest bond, zero in on those that have the highest bond order, because that's going to be the most important factor. To give you an example, if you look at nitrogen, which can form compounds with single, double, or triple bonds, the difference between a nitrogen-nitrogen single bond and nitrogen-nitrogen triple bond is about almost 50%. So nitrogen-nitrogen single bond is going to be around 150 picometers, a nitrogen-nitrogen triple bond will be down around 100. So it's a very big effect when you go from single to double to triple. You're changing the bond length by a lot when you change the bond order. Now, more subtle effects can come into play when you talk about atomic radii. All right, so if we have to compare bonds that have the same bond order, So let's say we have more than one bond that has the same bond order, and we want to compare them to each other. We have to use atomic radii to tell us which one's going to be the longer or shorter bond. And so it's a pretty simple relationship. If you have larger atomic radii in the bond, you're going to get a longer bond. All right, because remember, at a very simplistic level, a covalent bond is formed when the electron clouds of two atoms come close enough to each other to overlap. If the two atoms are bigger, if they have a larger electron cloud, they're going to overlap at a farther distance from each other. And so there's a direct relationship. The larger the atoms, the longer the bonds they tend to form. So if you have to start comparing bond lengths for bonds that have the same bond order, you need to start thinking about the atomic radii, which then comes from the trends in the periodic table, and for the two that are bonded to each other. Now, a related topic is bond strength, which has sort of an inverse relationship to bond length. So bond strength is also known as bond dissociation energy. They mean the same thing. And remember, we've used this in a few different contexts now, and it's the energy that's required to break two bonded atoms apart, or more specifically, 1 mole of those bonds. It's usually reported per mole. So it's the energy required to break two bonded atoms apart. All right, so if we have a generic bond AB, whether it's single, double, or triple bond, the bond energy is related to the energy required to break this into individual atoms A plus B to completely cleave the bond. And delta H is what we call the bond energy for this, or the bond dissociation energy, bond strength. All those things mean the same thing. It's just the amount of energy required to break apart two atoms that are bonded to each other. All right, so there's a relationship between the bond order and the bond length, which is that they're sort of inverse related. So the shorter bond is going to be the stronger bond. So the shorter bond length gives you a higher bond energy. And then it then follows from that, because remember that bond order, as we increase the bond order, the bonds get shorter and shorter. So the higher the bond order, also then gives you the stronger bond, because that shortens the bond length, which is inversely related. So really, whether you're comparing bond lengths or bond strengths, you really need to only be aware of those two factors that influence it. The radii of the atoms that are bonded together and the bond order between them, and both of those are then related to the bond length and the bond strength. They just have opposite trends. Okay? So let's see an example of this. You have a bunch of bonds here involving carbon and chlorine. Which of the following has the greatest bond energy? All right, so when you're given a problem like this, it's the easiest thing to do is just to compare two at a time. It's hard to look at a list of 5 things and automatically pick out the one that's the biggest or the smallest or whatever. So we're looking for greatest bond energy here. All right, so as I said, what we should probably do for looking for the greatest bond energy is zoom in on the bond that has the highest bond order first, because bond order is the more important factor. So these are all single bonds. A and B are single bonds. So we have single. This is a double bond. Now we have to figure out what's the bond order in C2H2. So we have to draw a quick Lewis structure of that. It has this connectivity. And then, because carbon wants to have 4 bonds, we need to have a triple bond between the 2 carbons to complete the octet and satisfy all the formal charges. So this is going to be C2H2 has a triple bond. And then, of course, this is a single bond as well. So if we're just looking for greatest bond energy, then all we have to do is find the one that has the highest bond order first. There's only one of these that's a triple bond, so automatically we can just pick that as our winner, because as I said, the bond order is the most important factor. So if we pick that one, if we want to compare individual groupings of them, the first 2, carbon, chlorine, and carbon, carbon, just to give you some more details on how to analyze these. So remember, we have carbon, chlorine, and carbon, carbon. So which atom is bigger, carbon or chlorine? So we go to the periodic table. Chlorine is below carbon as we go down the periodic table. That's a large increase in radius, even though it's a little bit to the right. So we expect chlorine to be a larger atom than carbon. So that means the carbon-chlorine bond is expected to be longer, which means it's expected to have a smaller bond energy. So carbon-carbon bond energy would be bigger because carbon is able to bond to itself a little bit closer because the two atoms are smaller. So that one, if we compare carbon-carbon to single bond to double bond, remember that as we increase the bond order, the bond energy always increases. So you're going to have this relationship between choices B, C, and D, where as you increase the bond order, the bond energy increases. And then finally, if we compare a carbon-carbon triple bond to the last one, which is a chlorine-chlorine, very obviously this one's going to have a higher bond energy because it has a higher bond order and it has smaller atoms. So both things work in favor of this being the stronger bond. All right, so there are two factors that influence bond energy, but I think a good helping, hopefully a helpful strategy for these types of problems is find the highest bond order first, because that's the more important factor. All right, questions on that topic? All right, the last thing I want to talk about, if I have time, is bond polarity and polarity of molecules. This was another topic that I tended to get a lot of questions about as we were going through it. Okay, so for bond polarity, when do we have polar bonds? When we're talking about bond polarity, we're just talking about two atoms bonding to each other. We're talking about a single bond in that molecule, just two atoms bonded together. And so anytime the two atoms are different, you're going to have a polar bond. Alright, so in the previous example, all the carbon-carbon bonds would be nonpolar because it's two of the same atom, but all the carbon-chlorine bond would be polar because it's two different atoms. So anytime you have two different atoms bonded to each other, the bond will be polar. And that means that the electrons are not shared equally. There's an uneven distribution of electron density. But again, to help yourself out in problems that ask about bond polarity, look at, first of all, just the two atoms that are bonded to each other. If they're two of the same atoms, you know it's a nonpolar bond. If it's two different atoms, then you can classify it as polar. That's a really easy way to at least start narrowing in on things. Now, how do we rank polarity? Because very often we'll ask you questions where, choose the bond that's the most polar or the least polar. And what it comes down to is the difference in electronegativity, delta En. So the difference in electronegativities is going to allow you to rank whether a bond is more polar or less polar. The higher the difference gives you the more polar bond. And if the difference in electronegativity is 0, that's what we call a nonpolar bond, but there's no difference in electronegativity. Well, not exactly. So if a dipole moment refers to the whole molecule that all those bonds are part of. This bond polarity just refers to two atoms in a bond. We'll talk about bond polarity here in a second, but when we're talking about polar bonds, you're just comparing the two atoms that are bonded to each other, not taking into account the shape of the molecule and whether those individual bond dipoles cancel out or not. So if you have a nonpolar bond, it's really two of the same atoms. There are some atoms that are different but have very similar electronegativities, so those would give largely nonpolar bonds as well. But rigorously speaking, the only time you have exactly a difference of 0 is when you have two of the same atoms bonded to each other. So the way we do this then is we have a bunch of bonds here, sulfur, silicon, chlorine, phosphorus, chlorine, silicon, silicon. We want to know what is the correct order for increasing polarity. So as I said, the first thing we should look for when doing problems like this are if we have two of the same atom bonded to each other, we know it's going to be nonpolar. So this one here is nonpolar. So that by definition has the lowest polarity of these four choices. So we can automatically rule out any answers where this is not the first bond listed. So sometimes in multiple choice problems like this, use a little bit of game theory to your advantage. So if we know that this is our only nonpolar bond, this has to be the least polar. You can't get less polar than nonpolar, if that's not obvious. And then, so look at all these answer choices. The only one that's going to be correct is one where this nonpolar bond is listed first in the ordering. So we can get rid of choice A, B, and C right off the bat because those ones don't have the nonpolar bond listed first. All right, and then from there we can consider the rest of them. So if we compare sulfur chlorine to silicon chlorine and figure out which one is more polar, it turns out all of these atoms are in the same row of the periodic table. We have silicon, phosphorus, sulfur, chlorine all right in a row here. So the one that's going to be the most polar is the one where the two are the furthest apart, left to right, because that's the direction that the electronegativity changes. So of these four atoms, silicon and chlorine are the furthest apart, so that's going to be the most polar bond. Okay, because when you're going across left to right, that's the direction that electronegativity increases. If you want the biggest difference in electronegativity, you need to pick the two that are furthest apart in electronegativity, which means furthest apart left to right if they're all in the same row. So this one's going to be the more polar of the two. Because they're further apart left to right. On the periodic table. So then the only answer choice that works is one where this one is more polar, or B is more polar than A, which is just going to be choice E. Because in choice D we have B listed, we have A listed after B, which is the wrong ordering of these two. We could also compare the other ones, A and or choice C as well, and see that this one has to be the most polar. So that means choice E is one that works out. So sometimes when you're doing problems like this, you don't necessarily need to think about all the answer choices. Try to find ones that you can eliminate based on something that's pretty obvious and go from there. So that's how we compare polar bonds. But the other aspect of this then is molecular polarity, which is the polarity of an entire molecule, whether an entire molecule has an imbalance of charge or not. And this depends on two factors. You must have polar bonds to have a polar molecule. So if we have all nonpolar bonds, like P4 or S8, phosphorus and sulfur, for example, as those elemental polyatomics, those can't be polar because they don't have any polar bonds. But if your molecule has polar bonds, it may or may not be polar. That's not enough. And the other thing we have to consider is the geometry. And remember, what we're doing with this is we're asking the question whether the individual bond polarities cancel out or not. Okay, because there are many examples of compounds that have polar bonds but are not polar overall because the bond polarities cancel out. Remember that something that is polar means it has a dipole moment. That's sort of two ways of saying the same thing. So if we go to this last example real quick, we're running out of time here. Which molecule is polar? In order to look at these, they need to have polar bonds, which all of these do, because they all have two different atoms in the structure. But then we also have to think about the shape of the molecules. So COF2 has a trigonal planar geometry. The best Lewis structure looks like this. So we have to be able to draw Lewis structures and also consider the three-dimensional shape of these. This one's trigonal planar. Normally trigonal planar is nonpolar, but here we have two different atoms. So you have large dipoles from carbon to fluorine. You have a slightly smaller dipole from carbon to oxygen. So they don't fully cancel out, and you're going to have a net dipole moment that goes sort of pointing down through the molecule like this. Okay? Because fluorine is more electronegative than oxygen, so the one oxygen is not able to cancel out the polarities of the two fluorines. So in this case, this one's expected to be polar. For all of the rest of these, for B, C, D, and E, B is going to be AX4. Anything that doesn't have any lone pairs is going to be nonpolar as long as all of the X's are the same. Choice D is going to be AX6, same story. Nonpolar as long as all the X's are the same when there's no lone pairs. And then E is going to be AX2, linear, nonpolar. The last one, which is not as obvious, is choice C. One thing we should remember is that all hydrocarbons are going to be nonpolar. Anything that just has carbon and hydrogen in the formula no matter what the geometry is, all hydrocarbons are nonpolar. So that one I didn't draw the structure, but we can just remember that fact. Never have to think about those ones again. So anything with just carbon and hydrogen has to be nonpolar. Okay, so the only one that works is choice A, which is the only polar one. So that's the topic I think we should definitely review. It will come up on the final. And then, like I said, Wednesday, Friday, and Monday we'll be reviewing more specifically for the final. If you have any last minute questions on this week's exam, I'll be around, so please come find me.